All right. So let's get started. So I'm Dan Freed. It's a pleasure to welcome everybody to the first of this series of 7 lectures on the Millennium Prize problems. This is a series of problems that was identified by the Clay Math Institute 25 years ago at the turn of the millennium. And this lecture series, which is jointly sponsored by the Department of Mathematics, by the Harvard Center of Mathematical Sciences and Applications, and by the Clay Math Institute. This series is designed to, again, bring these problems back to everybody's attention and to look at what's been happening over the last 25 years. So these 7 problems also each has a bounty of $1 million for the solution. And exactly one of the 7 problems has been solved in the intervening 25 years, and it's the one we'll hear about today, the 3-dimensional Poincaré conjecture. And there's nobody better to tell us the story of that 3-dimensional Poincaré conjecture than the fellow who solved the 4-dimensional Poincaré conjecture. And that's my old friend, Mike Freedman. In mathematics, we don't tend to give long introductions. This one has run way longer than most of them, which say the next speaker is Mike Freedman, and so here he is.
Thank you, Dad. Yeah, it's a great pleasure to be here. Those of you who know me will notice that I'm talking about the wrong Poincaré conjecture. I believe Perelman was unavailable, so I'm going to do the best I can. So the Poincaré conjecture is a question in 3-dimensional topology, and I'll try to ground it in the first slides. But it's remarkable. It was stated by Poincaré somewhat roughly in a few places around 1904, and it took roughly 100 years for Perelman to solve it using a really innovative method developed by Richard Hamilton, this Ricci flow equation. So I want to give you a sort of a understanding of the proof and also the context. That's my goal. But I said it's about 3-dimensional manifolds, and I know this is probably a diverse audience, so let's just start with 1-dimensional manifolds. So today the interesting manifolds will be compact, at least to start with. So in 1 dimension, there's really only one compact manifold. That's a circle. If you want to be pedantic, you could have disjoint unions of circles. So those are the 1 manifolds. After this point, maybe I'll stick with connected manifolds. In 2 dimensions, the list is very familiar. There's a 2-sphere, which I drew the same way as a circle, so please interpret it as a two-dimensional sphere. There's a torus, then there's a 2-hole torus and a 3-hole torus, and so on. And that turns out, up to diffeomorphism, to be an exhaustive list of the orientable connected 2 manifolds. There's another little list of non-orientable ones, starting with the projective plane. Just for fun, I drew sort of a schematic of how to make the projective plane. You can take the sphere, 2-sphere, and identify antipodal points. And a nice picture for that is to cut the 2-sphere into 3 regions, sort of a polar, northern and southern polar cap, and an equatorial region, indicated in green. And it's easy to see that the equatorial region, after you identify antipodal points, becomes a Mobius band, and the 2 caps become identified antipodally. So all you have to do to make the projective plane is to take a sewing machine and sew a disk onto a Mobius band along their 2 boundaries. It actually won't work with a sewing machine. The Mobius band will crinkle up and get in your way. But it's sort of a fun thing to try. Now, the Poincaré conjecture says that any closed, meaning compact and without boundary, simply connected 3-manifold is actually homeomorphic to R3. So homeomorphic is just a very simple thing. It means there's a continuous one-to-one correspondence between the points. So it's, think of it as like diffeomorphic, but without the differentiable structure. And then simply connected means that every closed loop can be deformed. It's called a homotopy in topology, can be deformed until it's a point. So strikingly, this test is exactly the same test in dimension 3 that you'd apply to surfaces to see if you had a two-sphere. That is, if every loop shrinks to a point on a surface, then it's a two-sphere compact surface. So the Poincare conjecture is that the same test applies in 3 dimensions, and you can, the little graphic here shows that the test at least works for the 3-sphere, because the 3-sphere is just Euclidean 3 space, 1 point compactified at infinity. And any loop that you draw in the 3-sphere, you can assume doesn't meet that compactification point. So that's that little red loop, and then you can contract it just by coning to the origin, if you like. So the Poincare conjecture is some kind of converse, that if this rule works, if you can contract loops, then the thing has that same topology as compactified R3. And this is a good moment for an aside that there is a Poincare conjecture in every dimension, so CPN, and beautifully they're all true. And this is called the generalized Poincare conjecture, and the test becomes slightly more complicated as you go up in dimension. As you go up in dimension, it's not sufficient to check that loops contract. You have to check that all maps of spheres up to the middle dimension contract. And if you have a closed manifold with this property, then the Poincare conjecture says it's homeomorphic to a sphere. There are many interesting subtleties in high dimension because famously there are the Milnor 28 7 spheres. So it's not true that it's differentiably the same. It's differentiably a sphere with this homotopy theoretic test. But in terms of homeomorphism, just continuous correspondence in every dimension, we have this result that conjectures a theorem. And the high dimensional case was proven first by Smale in 1959. And I did the 4-dimensional case leveraging really amazing and innovative work of Andrew Casson, his development of Casson handles, and Bob Edwards' development of decomposition space theory. So it's kind of curious historically that the last case, perhaps the hardest case, is the lowest dimensional case. It's really a very elementary question about 3 manifolds. It's sort of the first thing you'd ask. Now, although the statement of the Poincare conjecture is entirely topological, strikingly, the proof is through PDEs. There's not much topology in the proof. And Danny Caligari, my colleague at University of Chicago, summed this up as saying the proof of the Poincare conjecture is the greatest insult to topology. The differential geometers, the PDE people, took our best problem and solved it out from underneath us. So I want to explain, this insult in detail, and why it was worth 100 years of our collective time thinking about it. But before I do that, I just, this is a diverse audience. Not all of you are topologists or even mathematicians. I just want to step back and say a little bit about what mathematics is about, what it has been about, and is everything changing just as I speak? So, we all appreciate that AIs are really changing the landscape. And what Hamilton and Perelman did was really heroic, the boldness of these ideas. It's, like Mallory climbing or not climbing, we'll never know, Everest in 1924. And I got this email on this topic of AIs in math from Peter Doyle, and I have to say that I received this email a year ago, so it was kind of prescient. I think many people are thinking this now. This was like 13 months ago. And his email was in prose, but then I realized it was a poem. So I just organized the lines into as if it were a poem. And it goes like this. I've been thinking a lot about the Wright brothers lately because the idea that AIs will send mathematicians the way they sent Go masters seems about as unlikely as heavier than air flight. So we may be all at risk. Actually, yesterday, we had a distinguished speaker in Lecture Hall C, Jan LeCun, who still thought we have some breathing room as mathematicians, that AIs are more glib than intelligent, this is the quick summary. But let's see where we stand, in a couple of years. So I think of mathematics is about patterns, usually in very abstract spaces. And it has it consists of sort of a hierarchical way of compressing information, which is typified by nested definitions. A working mathematician typically is working, 10 or 12 definitional layers above whatever the foundational axioms are, Peano arithmetic or set theory. But they hardly notice, because the concepts they're dealing with feel like, family members. They're just completely familiar to them. But our efforts to teach AIs to do math really force us to consider what math is. Math seems to be somewhat different. Math as humans know it, somewhat different from just all the formal consequences of axioms, in some syntactic system. It seems to be a much thinner ribbon. And I think there are arguments that can be made that it's sort of a polynomial growth thing inside an exponentially large space. And the key example, and I'll talk more about this tomorrow actually in our little seminar at CMSA, but I think the key example is this observation of 3,000 years old, that you can express exponentially more numbers once you've discovered place notation. And if you think about that, that's a hierarchical set of definitions, because 10 is defined as 10 ones and 100 is defined as 10 tens and so on. And with these little extra definitions, you expand exponentially the ball of radius that you can work in the integers that you can work in notationally. And it's actually a kind of fun counting exercise to see that no comparable expansion exists if instead of the natural numbers, you take the free semigroup on, say, 2 generators. It turns out that with a logarithmic density of new definitions, you can hardly expand the radius at all, only a small polylogarithmic expansion. So there's something about slow-growing spaces like the line or the plane or a nilpotent group that enable definitional efficiency. And I think our experience with mathematics is that we rely on this definitional efficiency, and we can maybe make some conclusions about the geometry of mathematics. Well, maybe not. The age of heroic achievement is passing, and that we'll become AIs will become our assistants, and then soon we'll become their assistants. We don't know, but even if the age is passing, that's all the more reason to celebrate what's recently happened. Hamilton's and Perelman's work, and that's what I want to convey today. So the general picture I have of mathematics is kind of this lofty willow tree. And I think of it as a willow tree because even if it's very tall, it has this beautiful aspect that it often has boughs that are near the ground, and children like us mathematicians can run around and jump for the limbs and try to grab at the low branches. And I think of like the trunk is coming up from the axioms, and the branches are like our deductions, and we get to the theorems, which are these leaves. And I think we really want to know what mathematics looks like. What's the geometry of this tree? What are the statistical properties of typical proofs, and how do the proofs that humans discover and catalog, how do they differ from all the possible proofs? So I think that's an area of exploration that is natural in sort of the new realm. And I want to pursue this metaphor of the willow tree just a little bit farther before going back to three-dimensional topology. I'd like you to imagine walking up to the trunk of the willow tree and standing underneath it and looking up at the sky. And depending on exactly the details of the tree, how leafy it is, you may or may not be able to see flecks of blue sky, so do you see sky or not? And well, in my metaphor, I'll say no one knows whether you see any sky. And the metaphor is that the blue sky, if you see any, those are statements that the proofs, the branches and the leaves don't kind of get to. So they're like holes in mathematics. Are there holes in mathematics? Or let's just think of arithmetic. Are there statements in, where there's a standard model and we know what we mean? Are there statements in arithmetic which are true? They don't have any counterexamples, but they also just don't happen to have any proofs. Well, we of course know there are some statements like that because of Gödel incompleteness and self-reference. But what about the most ordinary statements like the Goldbach conjecture that every even integer is the sum of every even integer 4 or greater is the sum of 2 primes? That looks like it could be a statement that's true purely by accident, because once you've passed the first billion integers and haven't found a counterexample, the chance of finding a counterexample after that is, by some way of reasoning, extremely rare, because you have this logarithmic density of primes, and there's so many possible pairs that could add up to your even integer. I mean, these randomness arguments have to be taken with a grain of salt, but it suggests that once you've passed a billion, you're not at much risk anymore. So, but on the other hand, that's not a proof. It just means the risk was low and you were lucked out in the low numbers. Maybe there's no proof of things like that. So I think thinking about the geometry and structure of math sort of opens up new lines of inquiry, not necessarily productive ones. Okay, so now to the millennial problems. As Dan mentioned in his introduction, 25 years ago, 7 problems were set forward by the Clay Foundation. And 5 of them, I'd say, are core mathematical topics: complex analysis, algebraic geometry, topology, PDE. 2 of the problems are kind of outliers. They're more meta-mathematical. They're like, how much can mathematics tell us about other things? One of the problems, which I think Arthur labored over, getting the statement just right, really is a surrogate for asking, can mathematics describe physics? So this is the mass gap problem in Yang-Mills, but just in general, can you make field theory rigorously constructive and take continuum limits? And the other problem, is the P versus NP problem, which is really about, can mathematics develop a full theory of algorithms, or will it always be kind of this relative thing that we do today? Well, in contrast to the other lofty problems on this list, I'd say the Poincaré conjecture is strikingly down to earth. It's like the simplest thing you could ask in topology. Well, hence why the topologists felt so insulted when the PDE guys solved it. But so it's totally basic. So let me just orient you a little bit to closed 3 manifolds, because you can't really enjoy this conjecture until you've thought of a few examples. So the first one you might think of as the 3-sphere. We've already met that, the 1-point compactification of R3. Another very cheap and easy thing you can do is you can take the Cartesian product of 3 circles. This is like the generalization of the torus. That's another handy manifold. Or you could take a circle across any surface to bump up the dimension. Another example, we met RP2, 2-sphere modulo antipodal points. There's also RP3, which is an oriented 3 manifold, which is the 3-sphere modulo antipodal points. Now, all these examples I've mentioned to now are kind of arcane from the point of view of modern 3-manifold topology. Modern 3-manifold topology is really based primarily on insights of Bill Thurston, I'd say. And it's that the hyperbolic case is the generic case. So I took this tessellation of hyperbolic 3-space from the Clay Foundation website. So let me just say what hyperbolic space is. Euclid had this parallel postulate thing. And of course, it's not necessarily it's not implied by their axioms, and you have models of geometry that disobey the parallel postulate. And the most symmetrical examples which exist in the same topological space, so the plane, three space, four space, the most symmetrical examples which have multiple parallels through a given point, those are the hyperbolic spaces up to scale in every dimension. And if you've admired Escher drawings, he's using a particular model for the hyperbolic plane called the Poincaré disk model. And I have those slides. And I'll talk about sectional curvatures later, so I just wanted to introduce the concept. Riemannian geometry has a lot of different notions of curvature. Sectional curvatures are like in every two-dimensional direction, sort of what's happening. In a two-dimensional direction, are the geodesics converging or expanding? You know, are they expanding faster than in Euclidean space or slower? And those two cases are negative versus positive curvature. So constant negative curvature is the hallmark of hyperbolic space. And here I've drawn, like in the two-dimensional case, in this Poincaré model, what the geodesics look like. The model is a disk, but the straight lines in it are arcs of circles which meet the boundary of the disk perpendicularly. And the little arc that's disjoint from the other two, that's an example of a parallel to either of them. But you can rock that arc back and forth slightly, so you can see there are infinitely many possible parallels. Here's an Escher picture. So I mentioned that the hygenus surfaces were an example of negative curvature, or I should have mentioned it. It turns out that if you take a two-dimensional tessellation of the hyperbolic plane, and it has a regular tessellation, and it has a symmetry group by a standard theorem in number theories, theorem of Selberg's actually, there's subgroups of finite index which are torsion-free, and if you divide out the hyperbolic plane by such a torsion-free group of symmetries, you'll get necessarily a closed surface. So the higher genus surfaces all arise this way. They all come with hyperbolic geometry. So the sphere has a spherical geometry, the torus has a flat geometry, and the higher genus surfaces have negatively curved geometry. It's actually possible to visualize a hyperbolic manifold, at least get pretty close, by doing a similar kind of Escher thing. That little spiky thing that looks like something you might encounter in the ocean off Australia and wouldn't want to touch. What that's a picture of is a dodecahedron, which has been expanded in the hyperbolic model until its dihedral angles, as you expand it, they become tighter, sharper. And in Euclidean space, the dihedral angle is about 108 degrees for a dodecahedron. And as you expand it, there'll be a point where they're all 90 degrees. And stop there, and then you can build a reflection group. And then any finite index subgroup without torsion will give you a hyperbolic manifold. So that's like the easiest hyperbolic manifold to make. And it's probably related to this picture from the Clay website. So it's remarkable that often in mathematics, it's better to solve what seems like a harder problem. You want to put the problem in the right context. And although it's technically possible to prove the Poincaré conjecture by itself by PDE methods, it's very unnatural. When you start thinking about the PDEs and what you can prove, it turns out that there's amazing insight of Thurston. His conjecture about geometrization takes hold. So Thurston conjectured that every three manifold can be broken into pieces which geometrize. And I have a list of these pieces on the next slide, I think, or slide or two. Turns out that there are 8 types now. It's not just curvature, positive, 0, negative, but there are additional types of mixed curvature. But these types all have beautiful local models. They all have finite volume homogeneous spaces. And so there are 8 of these in dimension 4. And Thurston's conjecture, called the geometrization conjecture, is that every closed three manifold can be cut up into geometric pieces. So the way this works is first you have to get to prime pieces that are not connected sums of different types. And this is done by what's called surgery on two spheres. So you have to allow, when you find a two sphere, the ability to cut the manifold along the two sphere and then repair the damage by putting in two disks. So that's the first reduction. And then there's a reduction using tori, which corresponds to something called the JSJ, the Jaco, Shalin, Johansson decomposition in three manifolds that was previously known. So you have to cut along tori and then you find these geometric pieces. But Thurston's approach was by two-dimensional analysis. You know, he used complex analysis, complex dynamics, Teichmüller theory. He was really bootstrapping his way up from a comprehensive knowledge of the two-dimensional world. And he needed kind of a toehold to start this climb. So he couldn't get to the Poincaré conjecture. He needed an incompressible surface. So he was able to prove geometrization in, depending on your perspective, like half the cases or 90% of the cases. Many, many cases he proves geometrization. But he can't do certain cases because he can't begin. So the conjecture, the full geometrization conjecture was finally proved by Grisha Perelman following this Hamilton's equation, which I'll describe brief in just a moment. And I think the insult that Caligari mentioned consisted of Hamilton and Perelman discarding like 90% of the topologist's efforts. Like it wasn't that they conserved all of Thurston's amazing constructions and ideas. They kept a little bit of free manifold topology in there, but most of it they just brushed aside. Okay, so be it. But I think it is an interesting comment that it's often better to work on the more general conjecture. So at the end, the three-dimensional story kind of repeats the two-dimensional story repeats itself in 3D. We have these extra 6 pieces, which I enumerate here. In addition to spherical, Euclidean, and hyperbolic, we have pieces which are described by different homogeneous spaces, nil, PSL2, solve, and products. But we don't have to get into them in too much detail. So finally, Hamilton's equation. Maybe just one point. So Hamilton, I want to say that even though topology was used in higher dimensions and PDEs in 3 dimensions, in a sense, even the topology arguments in high dimensions also had a physical underpinning, which was Morse theory. You know, that's what Smale used. And you know, Morse theory is nothing more than how honey would like flow on the manifold if you covered it in honey. It's just, you know, like, just picture how the topology is sort of shaped out by watching something flow down the manifold. And Hamilton's equation, which is that the time derivative of the metric is proportional to what's called the Ricci curvature, and I'll talk about that in just a second. But this equation can be given a direct physical interpretation in terms of shaking the manifold. It turns out that every Riemannian manifold has what's called a unique torsion-free Levi-Civita connection. So it makes sense to take an element of length and displace it in any direction, either perpendicular or parallel. And what the Ricci tensor tells you is what happens at second order to a bit of displaced element of length when you displace it randomly. If you just trace through the definitions, if you integrate over the unit sphere, you find that's what it is. It's a random displacement. So if you think that you just shake your manifold, and by shaking it, all the elements of length are moved in random directions, and they pick up the metric where they move, where they're moved to randomly, then that's Ricci flow. And it's also been described as melting the manifold. I mean, that's this Hamilton equation is basically the familiar linear heat equation in disguise with an extra nonlinear term. So it's both a shaking equation and a heat equation. And actually, it's a little bit loose to call it parabolic because it has an infinite dimensional gauge symmetry. Turns out that everything is conserved under reparametrization by diffeomorphisms. And this was a little bit of a headache for the pioneers, but de Turck observed how to remove the symmetry and then just make it the most standard type of parabolic equation. So I've mentioned Riemannian geometry. Just for those of you who are not specialists, Riemannian geometry just means that at every point in the manifold, you have its linearization, its tangent space. And Riemannian metric is nothing more than an non-singular inner product on that. So that's what Gij is. And it's just used to measure length. The length squared of a vector is just the contraction of the metric with the indices of the vector. And though the metric depends on coordinates, there are invariant objects that can be deduced from products of the entries in the metric and its derivatives. First the Christoffel symbols, and then using their derivatives, you can construct what's called the Riemann tensor. And the Riemann tensor is a 4-index tensor, which locally tells you everything about the metric, the geometry of the manifold. So it's sort of the full story. And the Ricci tensor, which I mentioned, which was the right-hand side of Hamilton's equation, just go back to it, the right-hand side of the equation. The Ricci tensor is simply a trace. You contract one of the upper with one of the lower indices of the Riemann tensor. So Hamilton's very naive. Richard Hamilton was a very modest guy, and he pretended never to have any deep insights. And he'd love to say things like, well, I wrote down the equation because both sides had 2 indices. What else would you write down? So that was his explanation. The indices matched. And when you expand in harmonic coordinates, you see something of this form, that the equation does become the familiar heat equation, with the Laplacian being the Riemannian Laplacian, plus a higher order nonlinear correction. And this analogy to the heat flow is very powerful because we all know that if you have a conductor like a piece of metal and you start with some initial heat distribution, which is uneven, different temperatures, different points, and you just leave it sit for a while, it'll all even out, right? And that's the idea of Ricci flow, is you start with this tensor, the metric tensor, and you let it flow for a while. Actually, in 3 dimensions, it hardly matters whether you picture the full metric tensor or just the Ricci tensor, because they turn out one determines the other. In higher dimensions, the Ricci tensor is a loss of information, but in 3 dimensions, it contains all the information. So it's very natural to think that what this heat equation is doing, I mean, the way Danny Caligari explained the insult to me, is he said the analysts say, forget about all this Thurston stuff. Just take your manifold and revolve it slowly over a candle until it falls into its geometric pieces. That's the proof. So in 2D, this works perfectly. If you take any metric on a surface and you evolve it according to Hamilton's equation, which is well defined in 2 dimensions, you just go to one of the 3 geometries and you're done. In 3Ds, because there are these 8 possibilities, it's a bit more complicated. But what happens is really magical. What happens is that when you follow the equation, in finite time, in finite time, 2 spheres may pinch off to points. So this topological idea that you first break it into the prime pieces, you don't have to think of that as a PDE person. It just happens. You just watch it. And then the next thing is, over a long time, the tori don't actually fully pinch, but they get smaller and smaller. So like the JSJ decomposition, again, it's just there. You don't have to insert it. And it's a guess that's very believable now after 20 more years, that Ricci flow is complicated by the existence of singularities, but it's believed and very much supported by recent work of Bamler and others, that you can define Ricci flow through singularities, and then it becomes an extremely canonical object. And this guess that you can define a very general Ricci flow, I think is now true, but or maybe not proved, but more and more evidence. The original proof of Perelman and proof of subsequent mathematicians that I'm going to touch on later are fantastically complicated because the general picture is not fully established. So there are many, many technical details. But as we learn more, the schema of the proof is becoming simpler and simpler. So Hamilton discovered, parabolic maximum principle, Harnack inequalities, but he had trouble dealing with mixed curvatures. His strongest result, some of his strongest results were in the positive curvature case, where he proved a special case of the Poincaré conjecture when all the sectional curvatures were positive to begin with. But that's not a fully topological statement. Final note is this idea of Ricci flow emerged in parallel simultaneously in the physics community through the idea of renormalizing a metric on a manifold. If you adjust the scale and think what renormalization means in terms of Gij, turns out you get, as a first term, you get Hamilton's equation with some higher order corrections. I think it's possible that if Ricci flow is actually, if the metric is renormalized properly, there are often choices in physics of how you do renormalization, that you'll get exactly Hamilton's equation. That's a question. So Perelman introduced many, many brilliant innovations, and I'm just going to touch on 3 of them. One is Ricci flow with surgery. So this looks like kind of an awkward thing. You don't actually try to go through the singularity. You wait till you're sort of near where the singularity is trying to form, and you interrupt the flow. You do some combinatorial operation under a lot of control, and then you start the flow again. The second one is a notion of parabolic volume, which I just want to hold out as an example of a brilliant definition, that carries a lot of load once it's discovered. And the other is, most differential geometers would turn up their nose at these Alexandrov spaces. This is like almost heading toward point set topology. These are just path metric spaces with certain combinatorial curvature properties, so less than the Riemannian world. But it turns out that when you take limits, when you take rescaled limits of singularities as they're developing, it's very hard to figure out whether these are smooth manifolds, but it's easy to see that they're Alexandrov spaces. So Perelman had previously worked in this kind of a little bit off the mainstream category of geometry, and it really served him well when it came to analyzing Ricci flow. Now, I want to kind of go back in my mind now 42 years, I think. I was in Hamilton's office when he was just bursting with excitement because he had just discovered the calculation I'm going to show you on the next slide. And the calculation shows that 2 spheres will shrink in finite time, as I mentioned. Tori will shrink, but more slowly. It'll take infinite time. And higher genus surfaces will tend to expand. So this thing about the connected sum and the JSJ decomposition is totally natural. So here's what Hamilton showed me. So you just start with the Ricci flow equation, and you ask, well, if you have a time derivative of element of length, then you can figure out what the time derivative is of an element of area, and then integrate it over the surface to get the time derivative of the area of a surface. So I just do the calculation here. The convention is the 1, 2 directions are tangent to the surface, and 3 is normal to the surface. So the Ricci 1, 1 is the sum of the sectional curvatures in the manifold in the 1, 2, and 2, 3 directions. That's just what Ricci 1, 1 is by definition. So when you, and similar for Ricci 2, 2. So when you just collect the terms, you get this integral that has, integrate twice the sectional curvature in the direction of the embedded surface and the Ricci curvature in the normal direction. So now we're going to look at something. So right now we're just thinking about what's the time derivative of the area of a fixed surface in the manifold. But now suppose the surface is not just a random surface, but I've kind of made it geometrically beautiful by taking the minimal surface in its class, like the minimal two-sphere or the minimal torus, which we know exists. Then the beautiful observation of Hamilton's is you can compare the first variation of the area of the surface under evolution of the metric to the second variation of the surface when displaced normally without changing the metric. And you get an inequality. And I've written it out here. So you start with the second variation formula where phi is a real valued function that just tells you in constant metric what happens when you use that function to push the surface normally off itself. And if you push a constant amount, then the grad phi squared term disappears. And you're just left with this Ricci, and the kappa are principal curvatures of the surface. Principal curvatures illustrated in this slide. If you have like a saddle, you have these two principal curvatures, kappa 1 and kappa 2. And the formula I'm about to use, the Gauss formula, is that the curvature of the surface is the sum of the abstract curvature of its tangent plane plus this thing coming from the second fundamental form, which is kappa 1 times kappa 2. And the conclusion from the calculation, which I'll now go back to, is that surfaces of positive Euler characteristics shrink fast, surfaces of zero Euler characteristics slowly, and negative Euler characteristic will expand. So the way this calculation works is under the stability assumption, which means that the second variation is positive. We get from Cauchy-Schwarz that the Ricci term is bounded by the determinant of the second fundamental form integrated over the surface. And then when you combine the two lines, star and double star, you get that the second derivative of the area of the surface is just a multiple of its Euler characteristic. So it's a negative multiple. So surfaces with positive Euler characteristic shrink, zero Euler characteristic are stable, and negative Euler characteristic expand. So it's a very simple calculation, but amazingly profound. So what does this mean in terms of the big picture? So here's like my schematic of a general three manifold. It has things I kind of drew as necks. Those are two spheres that want to pinch off in finite time. And then you have these genus 1 surfaces, tori, and they gradually shrink. So in a finite amount of time, some two spheres or some three spheres will pop off. That's this surgery flow with surgery. So you don't actually do the flow to the bitter end of a singularity formation, but you wait until you understand a lot about the geometry of the neck. Then you call timeout and you do a surgery and you reglue the caps with a lot of geometric care, and then you restart the flow. And then the other necks, which are tori in cross-section, they become cusps after a long time. And those are the hyperbolic pieces. And if there were any of the other 6 geometries besides spherical and hyperbolic, those are seen by collapsing of fibers in a ciphered fibered structure. That's called the collapsing case. So I said there were 3 things. I talked about Alexandrov spaces and surgery, flow with surgery. The third item on my list was a miraculous definition. And I think that good definitions, not just like place notation for numbers, but I think good definitions are the whole story almost in mathematics. If you erased everything else except the definitions, you'd have this ghostly outline and you could figure it out. I think that this definition handed to Hamilton and Yao might have been enough. I don't know. Probably not. There are a lot of things that Perelman did. But so what Perelman did is I'm just going to focus on something he calls reduced volume or parabolic volume. But in his papers, 2002 and 2003, he actually introduces 3 different quantities, 2 of which are entropies of one kind, and one is sort of a dimensionless volume, so-called. And what they are is they're critical coercive monotones. So monotone means it's something when you integrate over the manifold, it goes steadily up or steadily down. Critical means it's scale invariant. So when you do parabolic scaling, meaning you scale space as the square root of time, the quantity is unchanged. So it's kind of a critical quantity under scaling. And coercive is maybe the hardest part of all. This one quantity is supposed to prevent any entry in the curvature tensor from blowing up. So it's coercive, it controls everything, which is what PDE people like. They like to control, 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 control. So critical allows you to zoom in and understand singularities. Coercive is the control. And then the monotone nature, well, it tells you tons of things. It's useful in proving these no local collapse lemmas. But for instance, it rules out a possibility which was present until Perelman's work. The Ricci flow would just take you in a circle. But with this monotone, it can't happen, so it's a very wonderful thing. So just very quickly, what this scheme of the definition is, it's based on like this heat ball construction or heat kernel. You have to define a very clever notion in this sort of space-time of evolving three manifolds, a very clever notion of length, which is something like the length of a minimum, it's actually sort of like a length squared. You integrate or an energy. You take a arc from a given point in your space-time to an earlier point in space-time, and you look at its spatial derivative norm squared, but you measure it in the time, in the metric at which time it occurs. And then crazily, there's an additional correction, which is that scalar curvature thing, which probably took Perelman months to figure out why it's there, because it's not a monotone without that. But you define this notion of length, and then the volume is kind of this Gaussian thing, because remember, L is like length squared, really. So the integral volume, really, it's a surrogate for the actual volume of a ball of radius square root of tau back in time, tau from the point you're standing. So it's somehow telling you about how the volumes of these heat balls go, and goes under the evolution of the flow. And powerful theme in Perelman's work is that if you control volume, you control everything. That's sort of the theme. So the broad outline of the Hamilton-Thurston program is simply melt or shake the manifold until it either dissolves into geometric pieces or collapse into Alexandrov spaces, which you can also understand that process. Over the last 22 or 3 years, in the hands of other practitioners, Kleiner, Lott, Bamler, and many others, the proof has matured to constantly get closer to this conceptual outline. And as the proof has matured, it's been possible to derive many new facts. And there have been other accomplishments like classification of singularities due to Brindle, which turned out to be Bryant solutions, and very close, as I said, to a canonical flow. But one of the concrete theorems that's resulted in the last 20 years, since Perelman proved the conjecture in 2003, is what's called some people call it the generalized Smale conjecture. I've written it here as the generalized Hatcher theorem. So Smale, in the 1950s, as a young fellow, proved that the diffeomorphisms of the two-sphere deformation retract to the rotations of the two-sphere. And then, amazingly, Hatcher proved this for the three-sphere, and it's really it's amazing, amazing argument. And then a few people proved slight variations, like I think was proved to be true for RP3. The same thing, that the isometries of RP3 were deformation retracted with the diffeomorphisms. But now it's true for all homogeneous three manifolds. It's always true if you have a homogeneous geometry and you take the isometries within that, that's a deformation retract of all the diffeomorphisms. And I put the names in blue of topologists that prove various cases of this. So it's a whole army of people over 20 years. but they didn't get all the cases. And finally, using the heat equation, Kleiner and Bamler have gotten all the cases of this deformation retraction. And the proof is simple enough to sketch for you in terms of Ricci flow. At least let's do it in the case of either positive or negative, +1 or -1 curvatures, the spherical or hyperbolic. And the idea is that let's consider this little vibration. If you have the space of diffeomorphisms, it moves metrics around. And in particular, if it acts on a metric of constant curvature, then it pulls back a metric of constant curvature. And whether it pulls back exactly the same metric or not, that's a question of whether the diffeomorphism was an isometry. So the fiber of that little vibration are the isometries. Now, morally, if you had Ricci flow through singularities and you could just let it hum, what that would do is would give you this R. It would give you a deformation retraction from all metrics to the symmetrical metrics, because that's what Ricci flow morally is doing. It's making everything more averaged and more symmetrical. But it's very elementary and well known that the space of all metrics is contractible. It's just sections in a vector bundle, not non-zero sections, just sections. So this space over on the right, I guess it's your right, is contractible. Morally, Ricci flow says the base of the vibration is contractible. That says the inclusion of the fiber into the total space is a homotopy equivalence. So, of course, their paper is like 150 pages long, their last paper, and preceded by many papers getting around 100 pages each. So there are obviously details I'm omitting. And the important detail is that they don't really have Ricci flow through singularities yet, but my prediction is 10 years from now they will. And then the proof will really be that simple. So Ben Chow and Richard Bamler have been kind enough to introduce me, I think because they know I did some work in four manifolds, so they kind of confide to me their hopes and dreams. And hope and dream is that Ricci flow works in four manifolds and gives some kind of geometrization there, but we don't know the answer. And this is a very bold thing, because in 4 dimensions, the Ricci tensor no longer controls the full tensor. But still, you got this equation, Gij is proportional to Ricci, so why not try it? And one beautiful target for their program is what's called the 11/8 conjecture. So this is something many people in this room, have puzzled over. If you look at spin 4 manifolds, the most basic example is the Kummer surface. It has Betti number 22 and signature ±16. So this ratio of Betti number to signature is this 11/8. And we know that ratio can't be 1 because it's a theorem of Donaldson that you can't have spin manifolds with definite metrics. But how close can you get that to 1? That's been a question. And all of our experience suggests that 11/8 is the right answer. And Furuta proved, using work of Cliff Taubes, basically a 10/8 conjecture around 2001. And I don't have it on this slide, but Harvard's own Mike Hopkins and collaborators Shen, and Xu, close enough, improve this estimate, but there's still a gap. So what I say on the next slide isn't true. I said for 24 years we've been stuck, but Mike and his friends have helped, but we still aren't at the 11/8. But there's this intriguing idea that you could do Ricci flow and break it into pieces. You're hoping, the hope for Ricci flow in 4 dimensions is it'll land on Einstein metrics. Metrics where the Ricci tensor is proportional to the curvature, or to the metric. So if the Ricci tensor is proportional to the metric, at least in the closed case, you have this Hitchin-Thorpe inequalities, which are similar looking. It's not 11/8, but it's 12/8, but this is the closed case, and the limiting pieces would have boundaries. So it's a big conceptual, very bold, grand thought to evolve Ricci flow on a spin 4 manifold and watch it shatter into Einstein and collapsed pieces, and then use some topological knowledge to piece the 11/8 conjecture together from Hitch and Thorpe. So maybe, good luck. I hope they can do that. I'm a spectator. Now, just to kind of return to my starting point, what is mathematics? I would say that the best proofs are not judged entirely, by the mountain they climb, but by what comes next, what they inspire, the ideas that come further. And what we've already seen with Ricci flow is it's climbed these very substantial peaks, the geometrization conjecture, generalized Hatcher's theorem. So it's kind of a gold standard, and it's not content. The practitioners are not content with mastering the three-dimensional world. They want to take it to 4 dimensions and perhaps beyond. In fact, this idea of taking things beyond is actually how we know, I think, that math proofs are correct. Like when Wiles proved Fermat's last theorem with big help from Taylor, we didn't know it was true because someone checked every line of the proof, but 100 number theorists and graduate students immediately realized this was a super powerful technique, and they all wanted to get their own information about Diophantine equations by similar methods. So they worked over the methods brutally. I think that's how we learn things. And I think it's the same thing happened with Perelman's work, is that once Perelman did his work, well, it is true that there were many detailed expositions which filled in the details, but I think those people could have been fooled. I think the people who could not have been fooled are the 100 graduate students who wanted to make their own mark in the subject using the same methods. So, while a computer is satisfied with one lean certificate, for a formalized proof, that isn't the way, mathematics develops. Mathematics is kind of a web of interconnected thoughts and insights, many of which may be shaky or even wrong for a while. But the whole structure is held together over thousands of years. And we rarely make mistakes that last very long. So I think of mathematics as people practice it has the aspect of this vast error-correcting code. We don't always do everything right, but in bulk, from a distance, it's all right. And this reminds me, actually, of my first climbing rope. It was a gold line. Modern ropes are kern mantled. They're made from some very strong fibers protected from abrasion by an outer sheath. So there's a kernel and a sheath. The old ropes were simply twisted and spun, small groups of fibers twisted around and then more fibers twisted. So it's a very complicated braid. But the result of this braided structure was that if you look at any strand, it repeatedly comes to the surface. And you'll notice that after climbing for 6 months with your rope, that has this very pleasant feel to it, this very pleasant texture, this kind of golden fuzz. Of course, the meaning of that golden fuzz is each strand has been broken. So there's no strand in your rope that's longer than 6 inches or something. But still, it's perfectly reliable. And I did trust it with my life, and I'm still here. So thank you, guys.